All right, so now we're going to talk about simplicial maps, which you should think of as being the analog of continuous maps, but in the context of simplicial complexes. So simplicial maps between simplicial complexes are sort of a natural counterpart to continuous maps between topological spaces. Okay, so let's look at how you go about constructing one of these. So let's say we have K, it's like could be a simplicial complex, and then we enumerate all the vertices, right? Let's call that U0 all the way up to UN. Okay. And if you recall, any point in the underlying space of that complex is in the interior of exactly one simplex in K. Okay, so recall that for any x in the underlying space, right, it is in the interior of exactly one simplex in K. Okay. All right. So let's just assume, without loss of generality, that this particular simplex is spanned by U1 to UK. And you can, of course, renumber. It's like the vertices, so that's true. So you don't really lose anything by doing that. Right. So let that simplex be the convex hull of U0 all the way up to UK. Be the simplex. Okay, so what that means, it's like to be in the interior, if you recall, is that you can write X as the convex combination of U0 to UK with the additional property that all the coefficients in that expansion are positive, okay, not just non-negative. Okay, so then I can write X as the sum from I equals to 0 to K of lambda I ui, with the property that the sum of the lambda i's from I equals to 0 to K is 1, and the lambda i's are greater than 0 for I equals to 0 all the way up to K. Okay, so this is in some sense what is meant to be in the interior of a particular simplex. So what we're going to do now is that we're going to think of these lambda i's, which are the coefficients of the expansion, but we want to think of this as now being associated with x itself. So we want to think of it as a function of x, if you will. Okay, so I introduce, it's like what are going to be called the barycentric coordinates. So let bi of x equals to the lambda i's, and this is for the I equals to 0 to K. And then the remaining, it's like coefficients. So you imagine, instead of thinking of it as a sum from 0 to K, you can imagine thinking of it as a sum from I equals to 0 to N, right? So over all the vertices. And then, of course, it's like in that situation, you know, the coefficients associated with the other vertices, which are greater than K, is equal to 0. Okay, so I would say that bi of x is equal to 0 for I equals to k plus 1 all the way up to n. Okay. And of course, it's like more generally speaking, it's like x is going to be in some subset, it's like of the vertices, all right? And you can just again formally think of that expansion in all of them instead of just one. Okay, so then, okay, so this means that I can now write x as the sum from I equals to 0 to n now instead of k. Right, the barycentric coordinate associated with x, and then uy. So in a sense, this is a tautologous statement, right? I mean, I guess the best way to sort of think about this is that this is really what's defining bi of x for you, okay? It's this decomposition, okay? And then these bi's, these bi of x, right, are what we call the barycentric coordinates. Of x in the simplicial complex K. Okay, all right. So if you actually plotted out these barycentric coordinates, then you'll find that they look like things like hat functions, right? They vary linearly from one point to another, or one vertex to the other, and so on. So these are piecewise linear functions, at least on each of the simplices. Okay, all right. So what can you do with these barycentric coordinates? Okay, so I'm just going to leave this here. Okay, so I'm going to leave just part of it. So if you will, again, it's like the critical statement is this piece here, right? I mean, this is basically what's defining the barycentric coordinates for you. Okay, so what can you do with the barycentric coordinates? So the barycentric coordinates allow us to lift a vertex map. Okay, so what is a vertex map? Okay, so it's a map obviously from the vertex set of one of the complexes to the vertex set of the other complex, but you want it to respect the simplicial complex structure in some sense, okay, and the sense is that it has the property more or less that vertices of K get mapped to vertices of L. Okay. So let me rephrase that. Vertices of simplices, it's like in K, get mapped to vertices of simplices in L. The vertices of a simplex in K, right, get mapped to the vertices of a simplex in L. Okay, so if that's true, it's like then it's easy to convince yourself that this is going to set you up for a situation where essentially you're going to map simplices in K to simplices in L, right? And right now, all this vertex map is doing is mapping for you the vertices, it's like of one simplex to vertices of the other simplex. So what of course you need to do then is you need to extend this, it's like to the interior of the simplex, okay? And what you're going to do is, of course, you're going to use these barycentric coordinates to do the interpolation for you. Okay, so so it lifts this vertex map, okay? Okay, so this is in some sense the definition of what a vertex map is. All right, so it lifts the vertex map to a simplicial map. Okay, let's call it F, which maps the underlying space of one complex to the other. All right, and it has the property that it's piecewise linear and it's continuous. What we're going to basically see that it's linear when restricted to a given simplex. Okay, and it's given by the following. All right, so if you want to take f of x, right, what you're going to do is that you're going to take the linear combination with weights given by the barycentric coordinates. That's quite natural. Okay, so it's bix. And then, of course, you have to take linear combinations of things now, which are going to give you something in the underlying space of L. All right, so I have to map the vertices. Right, so I take phi of ui. Now this is in that space. All right, but then I reconstitute it with the barycentric coordinates. Okay, so basically what you have now is something which is linear when restricted to each of the simplices. So in light of that fact, we oftentimes actually refer to it as a map f from k to L as opposed to the underlying space. Okay, so since this map is linear on each simplex, right, we often write that it's a map f from k to L instead. Okay. All right. So that's again a simplicial map. As we see, it's based on first introducing this idea of a vertex map. It's like which maps vertices of k to vertices of L with the property that you respect the structure of the simplicial complex k and L by having the property that vertices of a simplex in k get mapped to vertices of a simplex in L. Okay, so once you have that, then it's a question of interpolating. It's like what happens to the vertices by using the barycentric coordinate as the interpolant, if you will. Okay, and so this leads to this idea of a simplicial map. Okay, so I'll just stop here for now, and then we'll continue in a little bit.